Good morning and welcome to our today's discussion. Today we'll be looking at a concept in statistics called random variables. Called what? Random variables. Random variable. And then in this discussion, I'll be abbreviating it as R.V. R.V. So in this discussion, whatever place we see R.V, we are making reference to random variable. So the question is, what is a random variable? Before we can clearly understand the concept of a random variable, it is necessary that we look at other concepts called random experiments. Called random experiments. Random experiments. Random experiments. What is a random experiment? A random experiment is any trial whose outcome or outcomes are not known ahead of what of the trial. That is what we refer to as random experiment. For instance, in the toss of what of a coin or in the flip of what of a coin, it is a trial, is equal an experiment. Its outcome, whether it's going to land with the head or whether it's going to land with the tail, is not known ahead of that trial. So it is called what? An experiment, a random experiment for that matter. In the toss of a die containing 6 faces, ranging from 1 to 6, it is not known whether the seed is going to land with 1 or whether it's going to land with 2 down towards to 6. So it is equally a random experiment. So a random experiment is defined as any trial whose outcome or outcomes are not known ahead of what of that trial. That is what we refer to as a random experiment. Then a set that contains all the possible outcomes of a random experiment is what we refer to as sample space. So there is also another concept which we are looking at here, and that concept is called a sample space. It is called what? Sample space. Which, of course, in this discussion, I'll be writing as what? As capital S. I repeat. A random experiment is a trial whose outcome or outcomes are not known ahead of what of the trial, while a set containing all the possible outcomes of this random experiment is what we call sample space. What we call what? Sample space. It is equally for us to know at this point in time that we are now going to look at now the concept of what of a random variable. So we are now going to look at what the concept of what of random variable. What is a random variable? Having known what is random experiment, having known what is called a sample space, what now becomes what a random variable? A random variable is a function, is a mathematical function that is assigned or that is defined on the sample space, which assigns numerical values to the outcomes of what of that random experiment. I repeat. While a random experiment is a trial whose outcome or outcomes are not known before the trial, the sample space is a collection of all the possible outcomes of this random experiment. While a random variable is a mathematical function that is defined on the sample space, which assigns numerical values to each item in the sample space. That is what we call random variable. Mathematical function. It is defined on the sample space. Its duty is to assign numerical values to each of the outcome in the sample space. Then we equally have another concept which we call the range space, which we call the what? The range space. The range space is equally a set that contains all the possible numerical values that are assigned to each item in the sample space. There is difference between this sample space and range space. The sample space is a set containing all the possible outcomes of a random experiment without laying emphasis on whether they are numerical or not. While the range space now is a set containing all the possible numerical or real value of what? Of the sample space. That's what we call range space. And then in this discussion, we are going to be writing this range space as what? R subscript what? X. Where, of course, this X now is what we call the random variable. So we can equally have somebody write R subscript what Y, where the person is referring to this Y as the random variable. So that is what we call the range space or then the sample space. Sorry, the range space or the sample space. Now, these random variables, which of course we are discussing, is categorically classified what into two, based on the nature of the sample space or on the nature of the range space. So we talk about what types of random variable, types of random variable, types of what R dot what dot V. Like I had earlier said, that this random variable is categorically classified into two. And the classification is on the basis of the nature of the sample space or on the nature of the what of the range space. And the two classes of that random variable are number one, we have what we call discrete random variable, discrete R dot V, and then what we call the continuous random variable, continuous random variable, continuous R dot what V. Our discussion today is going to center on the discrete random variable, and then the class that is going to come immediately after should be on the continuous random variable in order to make the discussion a lot clearer and understandable to our students. When do we say that a random variable is discrete? And when do we say that a random variable is continuous? A random variable is said to be able to be discrete if and only if is sample space or range space contains countably finite or countably infinite what items. I repeat, a random variable is said to be discrete if and only if is sample space or is range space contains countably finite or countably infinite what items or elements. That is when we say that a random variable is a discrete. What are the examples of discrete random variables? Examples of a discrete random variables. Number one, or let me say number A. Okay, the number of faces on a die. Number of faces on what? On a die. Number of faces. Number of faces on a die. Of course, the number of faces on a die, first of all, is countable because you can count them. And equally, number two, it is finite. Begins from 1 and ends at what? At 6. So in this number A I gave, it is countable and as well as it is finite. Number two, or number B, we talk about number of cars in a car park. Number of cars in a car park. Of course, number of cars there is countable. So number one, it is countable because we can count the cars there. And in most cases, the number of cars parked in a car park is always finite. So in this condition, we can equally assume that it is countable and as well as it is finite. Then we now come and say number C. In number C, we are talking about the number of houses, number of what? Houses in a particular village, a particular village, in a particular village. Of course, the number of houses in a village, of course, is countable. You can count them. And in most cases, equally, it is what? Finite, because you can exhaust the list of the number of houses in that particular village. Okay? Then we now talk about number D. Number D, we now talk about the numbers in the natural numbers. Numbers in natural numbers. Okay? Talk about numbers or in positive integers. Positive integers. Positive integers. Of course, positive integers begins from 1 and ends at positive infinity. In this case, it is still discrete. We can still equally count it, but the only thing we know is that it is infinite. We can never exhaust the list of that integers. So in this case, it is still an example of a discrete random variable, but in this scenario, it is countable, but it is what? Infinite. And that was why we said that a random variable is said to be discrete if and only if its sample space or range space contains countable finite or countable infinite what? Items or members. And then again, another example of this, which becomes what? E, is what we call number of heads or tails in a flip of a coin, in a flip of 2 coins, and in a flip of 3 coins down the line. So these are examples of a discrete random variable. We are now going to lay emphasis on how to obtain the sample space, how to obtain the range space, and equally obtain the probability distribution of a discrete random variable, making use of a flip of a coin, flip of 2 coins, and then flip of a 3 coins. So permit me to clean here while we talk about determination of the sample space, comma, the range space, and the probability distribution of flip of coins. Permit me to clean this. So talk about determination of what? Of 1. Talk about the sample space. Sample space. Talk about the what? The range space. Range space. And then talk about what we call the probability distribution. Probability distribution. Probability distribution of discrete random variable or of flip of coins, of toss of coins, toss of coins. Permit me to put this S in brackets because we can talk about flip of a coin or coins. So number 1, I am beginning with a flip of a coin, just 1 coin. So number 1 condition or number A condition, flip of a coin or toss of a coin, a coin, toss of a coin. We want to determine its sample space. We equally want to determine its range space and then determine its probability distribution. When you get a coin contains 2 faces, either the head or the tail. So when a coin is flipped and it falls, it either lands with the head or it lands with the what? And with the tail, and nothing more. So the sample space here is going to be the sample space is going to be a set. That set is containing, it either lands with what? With a head, or it will land with what? A tail. These are the two possible outcomes of a flip of a coin. Then we now talk about what we call the range space. We talk about the range space. First of all, we say let a random variable x count the number of heads in a flip of a coin. Let the random variable x be the number, of heads in a flip of a coin, Then its range space is going to be R of what? Of x. Because we have already defined that this random variable is x. And it stands for the number of what? Of heads in what? In a flip of a coin. So I will now say is set is this. We now come here. We ask ourselves here. At this particular position, what is the number of heads which we have here? It is 1. Just one head that we have there. So we now write what? 1, comma. We now come to this position. At this position now, what is the number of heads that we have here? There is no head here. And because there is no head here, it's as good as writing what? 0 heads. So I will now come there and write what? 0. I will close it. Do remember that in the set, the position of the members or elements does not change the what the set. So this range space is the same thing as writing what? R of x is given as a set of 0, 1. I will now close it. So this and this are the same in definition of what? Of a set. The position of what? Of the members or the elements does not alter the what? The set. Don't you see, while I earlier had said that the sample space and then the range space are different. Why the sample space is the collection of all the possible outcome of a random experiment, which in this context is the flip of what? Of a coin. The range space is the set containing the numerical values assigned to all the possible outcomes of what? Of the sample space. So why this is a sample space, this is what a range space. Then we want to determine the probability distribution. In the probability distribution, we talk about the numerical values of the random variable and then the associated probabilities of that random variables. So I now have this, what we call a probability distribution. Probability distribution. Probability distribution. Permit me to write DSTN as a distribution. So in that case, I have this, I have this, I have this, I have this, and I have this. Then I have this. This is my x. This is my P of x equals small x. I will explain what I mean by this. P of x equals small x. Then I will divide the line. The value of x here is what? Is 0. The value of x here is what? Is 1. So we want to go and determine the probability that this random variable x takes a value 0. That is where there was no head. And of course, you know that for you to determine the probability, you are talking about expected outcome all over total possible outcome. At this particular place where you have x to be what? 0, what it implies there is that there is no head there. So we now return to this particular sample space. And we come to this place where there is no head. How many items do we have that contains no head? It's only one of them. What is the total items in the sample space? 1, 2. Which means it's going to be expected outcome 1, all over total possible outcome, which is 1, 2. So it becomes what? 1 all over what? 2. Then we now come to this place. Where this random variable x now becomes what? 1. Is a place where we have now gotten the head. And the number of head there is what? Is 1. Then we now come to what? To the sample space. How many number of heads do we have here? Only one number of heads. What is the total items what in the sample space? They are 1, 2. So it is going to be 1 all over 2, which is 1 all over 2. Such that if you sum the probability of obtaining tail and then the probability of obtaining head, they are meant to give you what? 1. And 1 over 2 plus 1 over 2 gives us what? 1. Which, of course, completes that statement that the sum of all the probability must give us 1. Therefore, when we are told that a coin is flipped up and we are required to determine the sample space, determine the range space, and determine the probability distribution, this is what we now do. So we are quickly going to go over to the toss of what? Of 2 coins, determine its sample space, determine its range space, and determine its probability distribution. So permit me to clean this one. So this time around, we are talking about what? A toss of 2 coins. Number 2 or number B. A toss of 2 coins. Of 2 coins. We first of all determine its sample space, and then before we now determine its range space. Tossing 2 coins together is as good as tossing the first coin, picking it up again, and then tossing it now the second time. And of course, you know that when you are given 2 coins and you toss them together, it is possible that head comes out in the first one and equally head comes out in what? In that second one. And in that case now, you are going to rejoice of obtaining 2 heads. So in that sample space now, you are going to have a sample space like this. Sample space. And of course, you know that this my sample space is S. So my S is going to be a set of. Then head came up in the first one, and then head came up in what? In the second one. It is equally possible that now you throw the 2 coins up, they fall down, then head comes out in one, and then tail comes out in what? In the second one. So in that case, you are going to have what we call head and what? Tail. But of course, you know that it's not possible, it's not a must that head comes first. It is likely that tail comes head before the head. So in that case, you can equally have what? T, what? H. And then it is possible that you toss 2 of them, then you obtain tails in both of them. So in that case, you have what? Tail, and then tail, you close it. These are all the possible outcomes when 2 coins are tossed up together. You can either be lucky to get 2 heads, or you can get head and a tail, which can equally be tail and what? Head, or you can get what? 2 tails, nothing more. This is what we call the sample space. Then we now talk about what? The range space. The range space is now going to be the numerical values assigned to each of these outcomes of in the sample space. But before we talk about range space now, we define a random variable. We say, let a random variable x be the number of what? Of heads in the sample space. So in that case, we are now going to have the range space going to be that my range space, which of course we are talking about r of what? X, because our x is what we defined the random variable to be. So we open a bracket. We now come here. How many heads are here? There are 2 heads that are here. Because this random variable x is counting the number of what? Of heads. Or the random variable x is now the number of what? Of the heads. When we come here, the number of heads is what? Is 2, comma. When we come here, the number of heads is 1, comma. When we come here, the number of heads is what? Is 1, comma. And when we come here, the number of tails is what? Is number of heads here is what? Is 0, because there is no head here at all. But then, if you do remember, the definition of this range space is a set. That it is a set containing all the numerical values. And of course, you know that in set, we don't repeat what numbers. Which means I'm going to define that this is going to be a set. Here is what 2, here is what 1, and here is what 0. Because I don't want to repeat this one. Otherwise, it ceases from being what a set. Which means when two coins are tossed up together, this is the sample space, and then this is what we call the range space. From this range space now, we can talk about what we call the probability distribution. In the probability distribution, which is number 3, or which is the third thing, probability distribution. Probability distribution. Okay? We are now going to talk about what? A table that goes this way, that goes this way, goes this way. Then we have here, this is our x, this P of capital X equals small x. We now have this way, we have this in this way. The list of it here is what? 0, 1, and what? And 2. When we talk about what 0, we are referring to a place where there is no head. And this is the only place where there is no head. Only one item is there. It's only one here. And how many items do we have in the sample space? 1, 2, 3, 4. So it is going to be 1 all over 4. That is expected outcome all over total possible outcome. So which means that place I'm going to have what? 1 all over what? 4. When we have 1 here, it is referring to a place where we have only one head. And if you come here, there is one head here. And if you come here, there is one head here. So inside this sample space, there are 2 items where we can see head. This is number 1, this is number 2. Which means the 2 of them are here, 1, 2. And the total item in the sample space is going to be 1, 2, 3, 4. So which means in this case, it's going to be 2 over 4. And 2 over 4, of course, is what? Is 1 over 2. So which means I have here to be 1 over 2. This is 1 over what? 2. And then when we now talk about 2, we are talking about that place where we have only 2 heads. We have 2 heads here. So when we come here, this is the only place where we have what? 2 heads. So it is 1 all over 4. Which is what? 1 all over what? 4. Therefore, when you are told that 2 coins are flipped up together, and you are told to determine the sample space, determine the range space, and determine the probability distribution, this is what, of course, what you do. And of course, you know, if you sum 1 over 4 plus 1 over 2 plus 1 over 4, it is expected to give you what? 1. The total probability is always what? 1. So the probability of getting double head tails, probability of getting one head, and then probability of getting 2 summed together is expected to give you 1. Thank you very much. I want to believe that I have not had any challenge. But if you have, please drop your worries in the comment section. We'll come across it and we'll address it for you. Don't forget to subscribe for more classes. While we go over now to the toss of what of 3 coins. So permit me to clean here. And before I clean here, it is important that I note this. We can equally have a random variable x that counts the number of what? Of days. The same thing is what we are going to get here. Look at it. If you say that the random variable x is counting the number of what? Of days. If you come here, there is no tail, and it is going to be what? 0. If you come here, there is one tail and there is one tail. So you have 1, 1. If you come here, there are 2 tails, and it becomes what? 2. We don't repeat number in a set, so it is going to be 0, 1, 2, which is the same thing with this. So when the question says the random variable x is the number of what? Of heads, or the random variable is number of what? Of tail, you are going to arrive at the same sample space, you are going to arrive at the same range space, and you arrive at the same probability distribution. Thank you very much. Permit me to clean this. So we talk about the toss of 3 coins. The toss of 3 coins. 3 coins. Okay? We are going to use something to illustrate this to make his understanding a lot faster. And that thing is, if I give you 3 coins and you toss all of them up together and they fall down, it is possible that you get 3 heads in all of them. And in that case, you have 3 each. You have 3 each. It is also possible that you toss them up. You have 2 each in one and you have a tail in the other one. So in that case, you have what? 2 H, comma what? T. It is also possible that you toss 3 of them up. You also have what? Just a head and 2 tails. Then you have what? A head, which is H, comma what? 2T. It is possible that you toss them up. You didn't get a head at all. You got 3T. So what this thing implies is, in the first or you toss, it is possible you get all of them to be head. Here it is possible that you get, here possible for you to get 3 heads, no tail. Here possible for you to get 2 heads and a tail. Here possible for you to get 1 head and 2 tails. Here possible for you to get 3 tails. So the number of heads decreasing, while the number of tails what is increasing. So when you now come here under this place, here, we are now going to write them well. So here becomes what? Head, head, head. That's what this means. You getting 3 heads. Then you come here. You now get what? Head, head, and tail. But it is possible that this tail comes first and you have tail, head, head. It is equally possible that you have what? Head, tail, and head. So if you come here, there are only 2 heads and 1 tail, which agrees with this. Here there are 2 heads and 1 tail, which agrees with this. Here there are 2 heads and 1 tail, which agrees with this. So all these are possibilities under 2 heads and 1 tail. We now come over here. Over here, we are going to have what? Head, tail, tail. And it is possible tails comes first, tail, tail, head. And it is impossible tail, head, and tail. So here is 2 tails, 1 head. I satisfies this. 2 tails, 1 head. Satisfies this. 2 tails, 1 head. Satisfies this. All these are possibilities under this one. Then when you now come here, you have what we call tail, tail, and tail, which is 3 tails. So for us to determine the sample space here, we are now going to say that the sample space here now, our sample space now, sample space, which is S, sample space is S, is a set containing head, head, head. So I have head, 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 comma, head, head, tail, head, head, tail, comma, tail, head, head, tail, head, head, comma, head, tail, head, head, tail, head, comma. We enter this one. We have what? Head, tail, and tail, comma. We have tail, tail, and head, comma. We have tail, head, and tail, comma. We are done with this. We enter this. We have tail, tail, tail. We close up the brackets. Then we now count. 1, 2, 3, 4, 5, 6, 7, 8. So the number of elements inside this sample space is what is 8. That is to say that my n of what? Of S is equal to what? 8, which we call the cardinality of the sample space. Number of elements inside the sample space, it is what? It is 8. Okay? Now, we want to go and then talk about what the range space here. When we talk about the range space now, which of course is my R of X, is going to be. Of course, we are saying, okay, let us in this case now, say that this random variable X is the number of tails. Let us say like that. Instead of saying that it is number of what? Of heads. So we now come here. If you come here now, for us to count the number of what tails here, there is no tail here at all. So I am going to use what? 0 tail is there. We now come over here. Only 1 tail is in this one, 1, comma. Only 1 tail is here, 1, comma. Only 1 tail is here, 1, comma. We are here. There are 2 tails here, so I have 2, comma. There are 2 tails here, I have 2, comma. There are 2 tails here, I have 2, comma. Here, there are 3 tails. I'll write 3. I'll close the brackets. But of course, there are repetition of numbers here. So we don't actually refer this to set, so to say. So in that case, we are going to have that this is a set of what? 0, 1, 2, and 3. And then this becomes our range space. When x, the range space of what? Of x, where x is the number of what? Tails in the sample space. Then from this, we now talk about the probability distribution. Probability what? Distribution. The probability distribution in this case is going to be something like this. We have something like this. Then we have something like this. We have something like this. We have something like this. Then we have this. This is my x. This is my p of capital X equals small x. Then I have this way. This way. So here is my 0, here is my 1, here is my 2, and here is my 3. Of course, when we talk about what 0, we are talking about that place where we did not have tail at all. We come here. This is the only place where we did not have tail at all. And it is only one of them here, out of 8 of them. So it is going to be 1/8. So I have 1/8. 1 over 8. Then we talk about what? 1. This is a place where we have only one tail. We have one tail here. We have one tail here. We have one tail here. So there are 3 positions of items where we have only one tail. 1, 2, 3. 3 out of what? Of 8. So which is the 3/8. So we have 3 all over what? 8. Then 2 here means where we have only 2 tails. Here we have 2 tails. Here we have 2 tails. Here we have 2 tails. 3 out of 8. So it becomes what? 3 all over what? 8. Then we now talk about what? 3. Where we have 3 tails. This is the place where I have 3 8, which is 1/8. We have 1/8. Now, of course, the sum of all the probabilities is expected to give you 1. So this plus this plus this plus this will give you 1. And looking at this, it is true because the denominator is 8. So adding up the numerator, 1 plus 3 is 4, 4 plus 3 is 7, plus 1 is 8, which is 8/8, which becomes what? 1. So when you are told that 3 coins are flipped up together and you are required now to find the probability of the probability distribution, the sample space, and then the range space of that experiment, this is what you do. Thank you very much. We are now going to go over now into what we call probability distribution proper. Probability distribution. So we are able now to look at what we call the probability distribution of a discrete random variable. What I have just done here is the probability distribution of a flip of a coin. So permit me to clean this. So we now talk about the probability distribution. Probability distribution. Probability distribution. Okay. When we talk about probability distribution, we are talking about equally a mathematical function that describes the probability of a random variable. It is a mathematical function. It describes the probability of the outcomes of a random variable. That's what we call probability distribution. A mathematical function that describes the probability of the outcomes of a random variable without laying emphasis whether this random variable is discrete or continuous. And that's the reason why we are quickly going to have what we call types of a probability distribution. Types of probability distribution. Types of probability distribution. Of probability distribution. Permit me to write this in this way. This is probability distribution. Probability distribution is classified into 2, into what we call discrete probability distribution and into what we call continuous probability distribution. We have number 1, what we call discrete probability distribution. Discrete. Discrete probability distribution. probability distribution. And then another name of this discrete probability distribution is what we call probability mass function. You can equally call it probability mass function. Probability mass function. Mass function. Mass function. Probability mass function. And then this probability mass function is abbreviated as PMF. PMF. So anywhere you see in distribution theory or probability distribution where we talk about PMF, it is called probability mass function. Probability mass function. Another type of probability distribution is what we call continuous probability distribution. Continuous probability distribution. Or you can equally call it as a probability density function. You can call it as a probability density function. Probability density function. And this probability density function is abbreviated as PDF. As PDF. So the two types of probability distribution are discrete probability distribution and continuous probability distribution. Another name of discrete probability distribution, probability mass function, abbreviated as PMF. Another name of continuous probability distribution is probability density distribution, density function, abbreviated as what? As PDF. So the question becomes, because our discussion today will center on discrete probability distribution, just like we centered our discussion on discrete random variable. When do we say that a distribution is discrete? Okay? When do we say that a probability distribution is a discrete probability distribution? When that mathematical function assigns or describes the probability of the outcomes of a discrete random variable, we now say that that distribution is a discrete distribution. Permit me to remove what came up here. I repeat, when do we say that a probability distribution is discrete? When a mathematical function that describes the probability of the outcomes of a random variable is limited to describing the probability of the outcomes of discrete random variable. We call such things what we call discrete probability distribution. And then both this probability mass function and then probability density function, we are going to write in this our discussion that our PMF will be written as what? P of capital X equals small x. Then for our probability density function, we are going to write as F of what? Of X. So this P of capital X plus small x is a probability function, PMF, probability mass function. This one is a probability density function. The underlying fact there that both of them is describing probability. And probability has a characteristics. And because probability has a characteristics, equally they should have a characteristics that align with the characteristics of a probability. Which means we talk about the characteristics of a PMF. Characteristics of PMF. Characteristics of PMF. And then equally we talk about the characteristics. The characteristics of PDF. Number one characteristic is that probability that capital X equals small x is always greater than or equal to what? 0. Probability doesn't take a negative value. So this is number one property of PMF. Then number two, we have that 0 is less than or equal to P of capital X equals to small x, which is less than or equal to what? 1. The probability, the PDF, which is the probability mass function, it lies between 0 and 1 inclusive. So the probability value doesn't go below 0 and it doesn't go above 1. So anytime you solve probability and it shoots above 1, know you quite right that it is wrong. If it goes less than 1, know you quite wrong whether it is wrong. Then we now have number 3. We say that sum over the range of x of P of capital X equals small x must give us what? 1. Which means the sum of the PMF over the range of that random variable x must give us 1. The same thing applies here, that number 1, that f of x is greater than or equal to 0. Number 2, that 0 less than or equal to f of x less than or equal to 1. And then number 3, that integral over the range of x of f of x dx is given as 1. This is sum for discrete random variable. This is sum for continuous random variable, which we are calling integral over this function must give us 1. This is what we call the properties or characteristics of what PMF, properties or characteristics of what of PDF. We are going to take 1 or 2 questions now on the PMF of a discrete random variable, and then we conclude the class to manage the size of what of the video. Thank you very much. Now, and I have to hint something. When this condition number 3 is satisfied, we call it proper PMF, or what we call true PMF. When we sum all the probabilities over the range of the random variable, and the answer is what? 1, we call it a proper PMF. When we integrate the PDF over the range of the random variable x, and the answer is 1, we call it proper PDF. So we are going to use this idea to solve some questions. So permit me to clean it. Let us solve some examples. Okay, let us take some questions I have here. The first question says, and I write, please permit me, let us write on the board to make sure that our students understands. Number 1, we call it solved questions. Solved examples. Let me call it solved examples. Number 1 says, let x be a discrete random variable with the following PMF. With the following PMF. With the following PMF, that P of capital X equals small x is given as I have here to be 0.1, I have here to be 0.2, I have here to be 0.2, I have here to be 0.3, I have here to be 0.2, and I have here to be 0. The condition here is for x equals 0.2, for x equals 0.4, for x equals 0.5, for x this 0.2, 0.4, 0.5, for x equals 0.8, for x equals what? 1, and otherwise. I will explain, so don't bother. The question says find a R of x, range of x, b P of capital X being less than or equal to 0.8, C, we have P of 0.25 less than X less than 0.75. And then D, we have P of X equals 0.12, given that what X is less than 0.6. Please let us explain. Okay. They ask us first, number one, they define the probability mass function as this. That the probability is 0.1 if the value of x is 0.2. The probability is 0.2 if x is what? 0.4. Probability is 0.2 if x is 0.5 down the what? The line. Up to what? Up to 1. And they say that the probability becomes 0 if it doesn't fall in any of these values of what? Of x. They ask us to find the range of x. And remember that the range of x is a set containing all the possible numerical values of the random variable x. These are probabilities of the random variable x. These are values of the random variable x. So these are the possible values of the random variable x. So a set containing all these possible values of the random variable x is what we refer to as what? As the range space. So therefore, my A, R of what? Of x is going to be a set 0.2, 0.4, 0.5, 0.8, 1. This is our A, the range space. Our B is probability that x takes a value less than 8. Look at our 8 here. So values of x that is less than 8 is 2, 4, and 5. So probability that x takes a value less than 8 is going to be, which is my B, P of x being less than or equal, okay, they say less than or equal to 8, is going to be P when x equals to 2, or when x equals to 0.4, or when x equals to 0.8, 0.5, or when x equals to 0.8. So it is going to be 0.2 probability that x equals to 0.2 plus probability that x equals to 0.4 plus probability that x equals to 0.5 plus probability that x equals to 0.8. You close it. That's what it is going to be. Because x must be less than or equal to 8. 0.2 is less than 8. 0.4 is less than 8. 0.5 is less than 8. 0.8 is less than or equal to 8. So, which means these are the conditions. Then we now say this equals. What's the probability when it equals to 0.2? 0.1 plus. What is the probability when it is 0.4? 0.2. 0.2. What is the probability when it is 0.5? 0.2. 0.2. What is the probability when it is 0.8? 0.3. 0.3 is equal to. This is 0.1 plus this 0.3, 0.5, and 0.8. So this becomes 0.8. So here becomes our x must be greater than 0.25 and our x must be less than what? 0.75. Less than 0.75. So we return here. It must be greater than 0.25. It must be greater than 0.25. Of course, here is 0.4. And that 0.4 satisfies that it is greater than 0.25. So 0.4 is there. 0.5 is here, which satisfies that it must be less than 0.75. It is only this 0.8 that is not captured there. And then 0.2 is not captured there. These two are the center, is captured there. Because 0.4 lies in this center. 0.5 lies in this center. 0.4 is greater than 0.25 and less than 0.75. 0.5 is greater than 0.25, but it is less than 0.75. So these two conditions satisfy it, which means my C is going to be P of 0.25 less than what? X less than 0.75 is now going to be P of X being 0.4 plus P of X being 0.5, which of course becomes 0.2 plus 0.2, which is equal to 0.4. Okay? Now, this is a conditional probability. This one is a conditional probability. And to solve the conditional probability, what you are going to do is number what? Number C. This is A, B, C, D. Number D. So to sum this thing now, we are going to have the conditional probability is written as probability of A given B is given as probability of A intersection B all over what? Probability of what? Of B. So you get where they have the intersection, then you divide with the probability of what? B. So you get where this x being equal to 2 and x being less than 0.6, where they have something in common. You now divide it with the probability of x being less than 6. So this is going to be, please permit me to clean here to complete that in there. Permit me to clean here, permit me to clean here. So this my number d now is going to be, this number d is going to be, this equals probability of 0x equals to 0.2 intersection x less than what? 6, 0.6 all over probability of x less than what? 6 inclusive. This equals. Now here x equals to 0.2, here x equals to less than 0.6. What does this and this have in common? Of course, you know that if x is less than 6, it means that this x equally here contains 0.2 because 0.2 is less than 6. So the only thing they share in common here is what? 0.2. There is 0.2 here, there is 0.2 contained here. So in that case, it is going to be probability that x equals to 0.2 all over probability that x is less than what? 6. You close it. Probability that x is 0.2 is 0.1. So this is going to be, this equals to 0.1 all over. Probability that x is less than 0.6 will come here. Less than 0.5 is less than 0.6. 0.4 is less than 0.6. 0.2 is less than 0.2. So if the probability of 0.2, 0.4 and 0.5, which is 0.1 plus 0.2 plus 0.2, which is 0.5. So this becomes 0.5. So that becomes this conditional probability. Okay? Permit me for a little rush just to manage the size of the video because it's becoming a little bulky and we still have another question to tackle. Okay? So if you have a challenge in all of this which we have done, please, I plead with you, drop your worries in the comment section because the interest for these classes is to make sure that some of these things that look abstract at times is brought clearer, more concrete to our students. Thank you very much. So permit me to clean this. Okay, let us solve this number together. We are going to be fast as well. Let's solve it together. That question says, and I write, the question says, okay, the question says, it said, let x, number 2, let x be defined, let x be a discrete random variable with PMF defined as P of capital X equals small x is given as this. Here is my K, here is my 2K, here is my 3K, here is my 0. They say for x equals to 0, equals what? 1, equals what? 2. And they say otherwise. The question here says A, find K, B, the PMF of x. The PMF of x. So that's a very straightforward question. We are told that a random variable x is defined this way. These are the probability of this random variable. When x takes a value 0, its probability is k. When x takes a value 1, its probability is 2k. When x takes a value what 2, its probability is what is 3k. They are asking us now what is the value of that word k. But if you remember something I told you about a proper PMF, the sum of all the probabilities over the range must give us what? 1. Okay? Which means that the sum, for me to solve that A, we say sum of x of P of capital X equals small x is given as what? As 1. For it to be a proper PMF. And then for me to over the range here means x is 0 here. When x is 0, what is the value of the probability? K plus. When this x becomes 1, what's the value of probability? 2k plus. When x becomes what? 2, what's the value here? 3 what? K. This, it doesn't have range here, so we can abandon the 0. Because even if you add 0 to this, it doesn't change anything. This equals to what? 1. K plus 2k is what? 3k. Plus 3k is what? 6k. You have that 6k is equals to what? 1. To make k subject of formula, we define both sides with the coefficient of k. All over 6, all over 6. This and this is gone, and k is equals to 1 over what? 6. So if k is equals to 1 over 6 now, what's actually going to happen at? We return back here. Here becomes 1 over 6. Here becomes what? 2 times 1 over 6. Here becomes what? 3 times, which means what I have here is P of capital X equals small x is given as this. In place of this k, what I'm going to write is 1 over 6. In place of this 2k, I'm going to say 2 times 1 over 6, which is 2 over 6, which is 1 over what? 3. In place of 3k, I'm going to say 3 times 1 over 6, which is 3 over 6, which is equals to what? 1 all over 2. Then here I am going to write what? 0. So that is how this probability distribution is. So here becomes what? 0. For this value here to be what? 0, value here to be 1, value here to be 2. So what am I going to do now? For me to find the PMF. PMF means I should come here and do here. PMF means probability distribution. I should do something like this, something like this, something like this. Do something like this way. Here is my what? My x. Here is my P of x equals small x. So here is my range. This is 0, this is 1, this is 2. What is the probability when it is 0? 1 over 6. So here is 1 over 6. What is the probability when it is 1? 1 over 3. Here is 1 over what? 3. What is the probability when it is 2? 1 over 2. Here is what? 1 over what? 2. Okay? So this becomes what we call the probability distribution. I'm sorry for the little rush towards the end of our class. It's because we intend to manage the size of the video so that you'll be able to access it on YouTube. Do not forget to subscribe to us. We are committed to bringing this abstract statistics to you in a way and manner that it has a flesh and you can easily relate with it. Thank you very much, and do subscribe to our YouTube videos for you to be getting our subsequent classes. Thank you very much. Meet us when we should be discussing the continuous random variable and then the expected value and variance of a discrete random.